Hello everyone. Today we are doing a design of linear integrated circuit, practical number 6, that is design of a comparator, zero crossing detector, time marker and a sample and a hold circuit. My name is Shah. His app ID is 6011180031. So let's begin. The simulation tool we have used today is LT-Spice. Our aim of this experiment is to design a non-inverting and inverting comparator, then design of an zero crossing detector, design of a time marker, and design of an sample and a hold circuit. So the op-amp comparator compares one analog voltage level with another analog voltage level or some preset reference voltage Vref and produces an output signal based on this voltage comparison. In other words, the op-amp voltage comparator compares the magnitude of two voltage input and determines which is the largest of the two. So we first study what is an inverting comparator circuit. In the inverting configuration, which is the opposite of the positive configuration above, the reference voltage is connected to the non-inverting input of the operational amplifier, while the input signal is connected to the inverting input. Non-inverting comparator. In this non-inverting configuration, the reference voltage is connected to the inverting input of the operational amplifier with the input signal connected to the inverting input. Zero crossing detector. Zero crossing detector is a voltage comparator that changes the output between positive Vset and negative Vset when the zero reference voltage. In simple words, the comparator is a basic operational amplifier used to compare two voltages simultaneously and change the output accordingly to the comparison. A zero crossing detector circuit is also used to produce an output state switch whenever the input crosses the reference and it is connected to the ground terminal. The output of the comparator can drive various outputs such as an LED indicator, a relay and a control gate. Time marker generator. For an input sine wave, the output of the zero crossing detector, being a square wave, is further passed through an RC uh, through an RC series circuit. If the time constant RC is well compared to the period T of the input sine wave, then the voltage across R of the RC circuit network called VR will be a series of positive and negative pulses. If the voltage VR is applied to a clipper circuit using a diode T, the load voltage V will always have only positive pulses and will clip away the negative pulses. Thus, a zero crossing detector, whose input is a sine wave, has been converted into a train of positive pulses at interval t by aiding a RC network and a clipping circuit. Sample and hold circuit. The sample and hold circuit are an electronic circuit which creates the sample of voltages given to it as input, and after that it holds this sample for the definite time. The time during which sample and hold circuit generates the sample of the input signal is called sampling time. Similarly, the time duration of the circuit during which it holds the sample value is called holding time. The main component, which is a sample and hold circuit, involved is a N channel and enhancement type MOSFET, a capacitor to store and hold electric charges, and a high precision operational amplifier. So we'll first see an inverting comparator with positive Vref, and it's different. Here we have done it on LT Spice simulation, and we have for different frequency, and we have found out the value of positive VSAT and negative VSAT. Now we'll see it in LT Spice simulation. So here we have the circuit. So first we'll do it for 50 hertz. So 50 hertz, we give it the simulation and we'll change it to 0.1 so we can see it clearly, and we'll run this circuit. So here we can see for the given for the given sinusoidal wave as input, we are getting an square wave as our output. Now we'll change the frequency to 10 kilohertz, 10 kilohertz, and we'll change the time to 0.001. We'll simulate this. So here we can see we are getting the output at a triangular wave. So now we'll see inverting comparator with negative Vref. So we'll open 6. So here we have a negative Vref. For in this also we similarly see for here we'll start with 500 hertz to see what is the output we get. So and we give the time period as 0.01. So we'll run this simulation. Go to V in and we give it to V out. We give it V in as we change it. We delete this place. So here we can see for the given wave we are getting an square. We are getting this as the output. We'll change the frequency to 5 kilohertz. We'll change this to 0.01. So here we can see that for our given wave we are getting a triangular wave as our output. Now we'll go to non-inverting comparator. So non-inverting comparator with positive Vref. So we'll open this. We close the inverting comparator. So here we have the non-inverting comparator. Similarly, like an inverting comparator, will give different values for frequency. So we'll start with 50 and to see what we get as an output. So here we'll change it to 0.1. So we can see it clearly. We simulate this. And we give it your V in and V out. So we can see we are getting a square wave as an output for 50 Hz. Now we'll change it to 10 kilohertz. And we'll change this to 0. We already given 10k. So we'll change this to 0.001 and we'll simulate this. So here we seem to have an output. I will delete this place. So we can see we are getting a triangular wave as our output for 10 kilohertz. Now we'll see non-inverting comparator with negative Vref. Close the positive one. So here we'll start with giving the frequency value as 1 kilo. We'll start with we'll first do 500 hertz. So we'll give it as 0.01 to see what we get in the output. So V1, V out. So again we can see we're getting kind of a square wave as in our output. Now we'll change the value of frequency to 5 kilohertz. Here we'll have to change this value. So we are giving at 0.01. So we can see we are getting a triangular wave as our output. So this was comparator. Now we go to zero crossing detector. Zero crossing detector. We close non-inverting comparator. So here we have zero crossing detector. Now we'll simulate this. So we are getting a square wave as our output for zero crossing detector. Now we'll see time marker generator. So here we have time marker generator. We'll close this. We'll simulate this. So we can see we are getting spikes as our output. Now we see uh, sample and hold circuit. So this is our circuit, and we'll simulate it. So we can see V in and V out. So this is our output for sample and hold circuit. So in conclusion, we can say that comparators, we'll see the different application. Comparators are often used to differentiate between two conditions in a system. Example, and an outputting a low logic high of 5 volts in an over voltage situation and a logic low of 0 volt for normal operation. Along with dedicated comparator, it is possible to configure operational amplifier op-amp to operate as comparator. Applications of zero crossing detector. Zero crossing detector circuits can be used to check the condition of an operational amplifier and also used as a frequency counter and for switching purpose in power electronic circuit. ZCD as phase meter. A zero crossing detector can be used to measure the phase angle between the two voltages. A sequence of pulses in the positive and negative cycles are required to measure the voltage between the time interval of the pulse of sine wave voltage and second sine wave. This interval of time is related to the phase difference between the two input sine wave voltages. The use of phase meter ranges from 0 degree to 360 degree. Time marker generator. For an input sine wave, the output of the zero crossing detector being a square wave, further it will pass through an RC series circuit. If the RC time constant is very small compared to the time t of the input sine wave, and the voltage across R of the RC circuit called VR will be a series of positive and negative pulses. If the voltage VR is applied to a clipper circuit using a diode D, the load voltage VL will only have positive pulses and will clip away the negative pulses. Therefore, a zero crossing detector whose input is a sine wave has been changed into a sequence of positive pulses at T interval by adding a network of RC and a clipping circuit. Sample and hold circuit are used in following applications: analog to digital conversion ADCs and in DAC. Out of different analog to digital conversions, successive approximation type ADC uses S by SH circuit where the signal is to be held constant while A to D conversion is taking place. In analog demultiplexing, in data distribution and in analog delay time. In general, sample and hold circuits are used in all applications, whether it is necessary to freeze the analog signal for further processing.